this video we look at the normal distribution. So a normal distribution is a common continuous distribution. So the continuous part is important. So meaning it's a continuous variable. And in this distribution, data are distributed symmetrically and unimodally about the mean. So to get an understanding of what that means, here's a picture of a normal distribution. So we've got this curve here. It's often called a bell curve because it kind of looks like a bell. We've got this bell curve coming up here. We can see that if this were the frequencies along the y-axis, so if we had these as frequencies, that the mode, the value that occurs most often would be right here. And it turns out that that's also the median. If this data is distributed symmetrically, then this point that's the highest point, this point here, sorry, that's the highest point, has to be the point that's in the middle because we have an equal amount to the left and to the right. So this is also the median, and it turns out that it's also the mean. It's in the middle. So that's an interesting property of a normal distribution, is that the mode, the median, and the mean are all the same. The other thing that you should note here, if we're talking about probabilities as areas under curves, and we'll get into this a little bit more later on, but just to give you some sense of what's going on here, we'll talk about areas under the curve. We talk about the area under this curve representing probability, and the total area then has to equal 1 because the probability of an event happening cannot exceed more than 1. So we'll get into some details on that. If you've looked at calculus, if you've done some calculus and you've looked at areas under curves, that's the kind of work that you do here. We're not going to get into the calculus portion of it, but we'll see how we can use the areas to find probabilities and how useful a tool that will be for us moving forward. So what kind of data might be represented by a normal distribution? Well, it turns out that there are lots of different types of data that can be represented by normal distributions, and these would be data that occur naturally or that we can find. So for example, if you were to look at a person's height, and let's just focus on adults right now because we know that children are quite a bit smaller and might skew things here a little bit, but let's just look at adult heights. And again, if we're talking about frequencies, we know that there are lots of people who would be in the middle, average height, and there are a few people that would be really tall, and a few people, when I say a few, it could be a lot, but there's a small number of people that are very, very tall, and a small number of people that are very, very short. So those are characteristics of a normal distribution. You get this kind of graph. If you took a large enough population and graphed the heights, you would get something that looks sort of like this. So one thing that you should note is that the data that you graph and look at may not give a perfect normal distribution. And here's an example. So this is an example of some simulated data. You can see the histogram here. It's not a perfectly normal distribution, but you can see that normal curve in here. I'll try to trace it out a little bit. You can see that normal curve in here that represents that bell curve. And you can see that this data can be approximated by this normal curve. It's not perfect. You know, there's some spots that are off by quite a bit, like right in here. But you'll notice here that there are some spots above the normal curve and some spots below the normal curve. And so we can sometimes use this normal curve as an approximation. One, because it's easy to work with, and two, that oftentimes it's not a bad approximation. Well, speaking of approximations, we can also use this normal distribution. Remember, we talked earlier about how a normal distribution is for continuous data. We can use it again to approximate discrete data. So we can use it to approximate discrete data such as a binomial or hypergeometric distribution that we've looked at before. So on the left here we see this graph here that is a this one I believe was a binomial distribution, and we can see the data plotted here and what it looks like. And you can see on the right here the red curve indicating that this looks fairly normal, has that sort of bell-shaped shape, I guess, and we can sometimes use that normal distribution to approximate either a binomial distribution or a geometric distribution. So let's have a look at an example here. We'll look at what the graph might look like, and then we'll get into some details. So here we have an example where we have the mass in grams of 21,000 potatoes. So a large number of potatoes is recorded. It turns out their average mass is 150 grams, and there's a standard deviation of 20 grams. So that average mass, just show that here. It's shown with a line in gold. That's kind of hard to see, but here's 150. There is the average mass of 150, and we kind of get this histogram that looks like this. Now you can see here that the normal curve doesn't fit very well. There are some sort of large gaps here, 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 and some fairly large portions that are above of the histogram that are above the normal distribution. Well, it turns out that if we change the interval size, so the interval size here I believe was 10, going from 115 to 125. So yeah, the interval sizes here are 10. If we shrink those interval sizes down to 5, you can see that the normal distribution actually looks a little, the distribution of the mass looks a little bit more normal. It seems to fit that curve a little bit better. So this was a 10 gram interval. This is a 5 gram interval. And down here we have a 1 gram interval. So it's the same graph, same data, just changing the intervals down here. And you can see that the data here fits that normal curve really, really, really well. It's not perfect, don't get me wrong, it's not perfect, but it does fit much better than the one up here did. So changing the intervals can make the graph sort of more normal. Now it's important to realize that we can't just keep making the interval size smaller and smaller and smaller and get a good approximation, because if we make the interval size small enough, we might get some sort of we might see a lot more bumps, kind of like this, where a certain interval doesn't have very much in it and that sort of thing. So there is an optimal size for intervals, and it totally depends on the number, on the situations. You know, you wouldn't want an interval size for each potato. Say if we had 21,000 potatoes, we wouldn't want 21,000 intervals because that would just look very bizarre. So that's important to keep in mind here, that although shrinking the interval size can help, there is a limit to how much we want to shrink. Alright, here's the power of that normal distribution. It is a curve, as I mentioned. We can find the area under that curve. That area can represent probability, and it turns out, again, through some calculus, which we won't get into, just because that's beyond the scope of this video, but it turns out that for all normal curves, any normal curve that you draw, 68% of the data will lie within one standard deviation of the mean. So here's the mean right at the peak. See if I can get there. Here's the mean right at the peak. And if we go one standard deviation to the right and one standard deviation to the left, we create this shape similar to like a relative frequency polygon that we might have looked at earlier. We create this shape, and it turns out that 68% of the data lies within this range right here. So right in here, we would get 68% of the data. So the probability of choosing a value in between the standard, one standard deviation either side of the mean, is going to be 68%. And that's what this information here says. Now, if we reach a little bit further, so we go another standard deviation out to the right and to the left, it turns out that 95% of the data lie within two standard deviations. So here's the mean. We went over one standard deviation. We went over a second standard deviation in both directions. And we find that 95% of the data lies within two standard deviations of the mean. Now we can take this one step further. We can actually keep going, but you can see here that once we get to 3 standard deviations, we're looking at 99.7% of the data. So going again one standard deviation further to the left and to the right, we see that 99.7% of the data is going to lie within this range right here. And we can use that information to help us make some predictions or determine some probabilities. Let's have an example here, or look at a couple of examples. So again, we'll use this example of the 21,000 potatoes. Just a reminder that the graph looks something like this. So we saw that it was sort of a normal distribution. could be approximated by a normal distribution, and that normal distribution looks something like this. Again, all normal distributions have that same bell curve to them. We know that there is a mean, and that happens at the peak, and that mean in this case is 150. We also know that the standard deviation is 20 grams. So if we go out one standard deviation in this direction, will be 20 grams further out. So 150 plus 20 gives us 170. We can also go one standard deviation in this direction. The standard deviation is 20. 150 minus 20 gives us 130. So here the question is asking us, if our x is our random variable, what's the probability that the mass of our potato, that's this x value, is between 130 and 170? Well, that's this part of the graph right here. Right in here. Well, this is one standard deviation here and one standard deviation in this direction centered on the mean. So we know that 68% of the data has to lie within that one standard deviation. So 68% of the data has to be between 130 and 170 grams. We do the same thing here for part B. It's asking about 110 and 190. I'll just see if I can do another graph here without getting too crowded. So it's a normal distribution. We had our mean at 150. We want to go all the way out to 190 and down to 110. Well, notice the difference from here to here is 40, and the distance from here to here is also 40. Now you might be wondering, what happens if the distances that we're looking for aren't perfect multiples of the standard deviation? We'll get into that a little bit later, but for now the goal is to just look at knowing those sort of 1 standard deviation, 2 standard deviation, and a 3 standard deviation benchmarks. What information can we find? So again, this is 2 standard deviations. Just a reminder that lowercase sigma represents standard deviation, so we're going 2 standard deviations to the left of the mean, 2 standard deviations to the right of the mean. That means that 95% of the data needs to lie within this interval right here. So the probability that we get information between 110 and 190 is 95%. And now let's change the question just a little bit. And the question is asking, what's the probability that the mass is less than 110? So I was just thinking if I could do this on the same graph that I've already done, but I think I'll draw another one. Kind of make it look like the Snapchat logo if you want. So here we are. We've got this distribution. We want to know the probability of less than 110. That happens in here. Well, we've already determined that 110 is 2 standard deviations away from the mean. So this is the mean here at 150. Now this gets a little bit tricky. So let's pay attention here and follow along. Here we have, this is what we're interested in, the probability that x is less than 110. Well, we know that half of the data lies to the right. So I'm just going to color this in. We know that this is half of the data. So this is 50% right in here. This green bit is 50%. Because it's half of the graph is symmetrical, and that's half. We also know that from here, the 110, maybe we'll use a different color for this, from the 110 to the 150 is 2 standard deviations. It's 40 grams from here to here, which is 2 standard deviations. Well, we know that 2 standard deviations should be 95% of the data. So 95% of the data should lie from this mark right here to this mark right here. Well, we've already counted this little bit here in the green, but we could just take 95% and divide it by 2, and we'll get this part right here in blue. So if we do that, I'm just going to jump over here. So we know that 95% divided by 2, so again, just finding half of 95% is 47.5. So 47.5% of the data lies right in here, and we know that 50% lies over here. That means that this stuff that's not shaded in red, oh sorry, I wrote this one as a percent and this one as a decimal. Let's fix that up. So that's this part right here. The stuff that's not in red is just the sum of 47.5 and 0.5. And the stuff in red, because the total area under the curve, so the total area under the curve has to be 1. All of this has to be 1. So the probability, just jot this down here because I've run out of space up there, that x is less than or equal to 110 is equal to 1 minus the area in blue, which is 0.475, and minus the area in green and blue, I guess, which was 0.5. So we can subtract those two, and we can see it's going to be small, obviously. So 1 minus 0.475 minus 0.5, and we get an answer of 0.025. So the probability that x is less than or equal to 110 is about 2.5%. And again, that's an approximation. So basically, these kinds of questions basically involve cutting up that bell curve, taking that bell curve and cutting it into pieces that we already know the values for, using that 68, 95, and 99.7 benchmarks, using those benchmarks and trying to sort of say, well, how can I use that information to find the information that I want to find? I like to shade in, as you saw here, shade in the area that I'm trying to find, and then I start looking at, well, how do I get this? Well, I can get that by doing 1 minus all of this over here. Sorry, it's getting a little bit messy on that diagram there. I think it's time to leave that one alone. So that wraps up our introduction to the normal curve. As I said, we're going to get into some more details about what happens when we're not talking about multiples of the standard deviation.